Alex, you're going to talk about a neat subject. We wanted to get this on a recording. Go ahead, please.
All right. Since it's too hot to set my telescope up outside, I've been going over some things that I could do inside. And one of the things is about LNA gain drift with temperature. I've seen lots of posts that say that LNAs drift with temperature. Keep them cool. As the night cool, the electronics work better. Heat makes an amplifier's gain drift. Ambient temperature changes will change the LNA amp gain. But I've never seen it quantified. So I thought I came up with an idea to try to quantify this, to see how bad is it really. And the test case was what is used frequently is the Salbird H1 LNA. And some of its significant characteristics is that it has some pretty good gain, 42 dB, has a reasonably low noise factor, and the SAW filter is defined to be good for H1, the H-line frequencies. So I use this I thought I'd do an analysis of this. And this was the setup. I used a nano VNA, and in the output, I ran this through I have a 3-stage cavity filter. And this was, I don't know what the shape of the excitation waveform out of the nano VNA. I know it's not a nice sine wave sweep. So if it had some strange characteristics, I thought I would smooth it out and at least just focus the excitation frequency over the range of interest. I imposed some attenuators going into the Salbird, and then the output of it, since it has a voltage on its output, since you could drive it with a bias T over the coax, DC block into the return of S2. And this is sort of a layout of what I did. Here's the cavity filter, and the output of it has the attenuators, and then going around and back, there is the DC block over here going into the analyzer. Everything was battery powered, so I could run this for hours. And this is an idea of one of the test setups, is that initially I used the refrigerator for 2 cold steps, for cool and cold. Found that this turned into an issue of kinking the cable. I had a lot of false starts. I probably ran this test 6 or 8 times. It wasn't as trivial as what I thought it might be. I ran a linearity test of both the Salbird and the nano VNA. And what I did, I just connected in and out from the Salbird back to the output of from the S1 to back into S2, and imposed a series of attenuators on the input to the Salbird. And the key is, as long as you have at least a 30 dB attenuator going into the Salbird, you have a pretty good linearity between 30 to 90 dB. And so I set up the system that I was running in the middle of this linearity. So I'll do this one more time, is that I took the output of the nano VNA, and I posed these various attenuators to the input of the Salbird and then back into the S2 channel of the analyzer. I did some measurements. I measured what the reading was of Earth and sky. This is from tests that I had done with actual data. And so I thought that I wanted to run 2 levels. And so I simulated about a 53 dB and a 63 dB, a 10 dB step. And so I ran a series of temperature tests at 2 different amplitude levels. only because I had never done this before and I didn't know what would be the appropriate way. So I thought I would try to sort of cover the amplitude range of that which I was measuring outside. And so the idea being, take the output, the S1 output of the nano VNA, you create a narrowband waveform or bandwidth here into the two attenuators to create the environment of either the cold sky or the earth, into Sawbird out, and subject the Sawbird to different temperatures and record the return amplitude. Did a lot of tests, and each test probably took about 4 hours to set it up, to stabilize at 4 different levels. Actually, it was 6 different levels, because I would stabilize at ambient, go, let's say, to the refrigerator, go to the freezer, back to ambient, make a measurement, then hot, and then back to ambient. So there are 6 different steps, half an hour between steps. So there's a good 4 hours per test. I had some issues initially that I threw all the early data away, because what I was doing was putting the coax into the doors of the refrigerator, and the internal molded shelving caused the cable to bend fairly sharply. And after several tests, I was getting some drifts, and evidently I had damaged the cables. So I threw the first cables away, bought a new set, and came up with a way that everything was stable, didn't bend any of the cables. This is what I got. 4 different temperatures, from 50 hot down to ambient, down to this would be about 10 or 11 C in the refrigerator, down to about -15 in the freezer. But I was surprised that the linearity was that good. And here was the surprising answer, is that the decibel change, the dB change per degree C, is really very small. The other thing that shows about 40 dB gain, which is proper with what the specification is on the no electric Sawbird, and so these seem to be pretty consistent. And so the slope of the line says like 7 to 8 thousandths of a dB per degree C. I got this data, I shared it with Bob Strickland, but I didn't know what to do with it. I didn't know how to correlate with this with anything to see if this was at all valid. But so there's another half to this, in that he sent me this. He had taken apart the Sawbird and identified the LNAs as being a 9037. And so doing a little research, I found this Corvo has these 9037 ultra low noise, high linearity LNAs. And if you look at the specs, it has a right frequency range, it has a low noise factor, and it has 20 dB. Since the Sawbird uses 2 chips, that gives you about the 40 dB. So we'll presume this is the right part. And Mouser has the data sheet. This has a huge collection of plots. I was surprised it's as well characterized as it is. And it's also cheap. So in large quantities, you can get it down to probably $1.50, which would be appropriate for the Sawbird. One of the plots shows this gain versus frequency, but there's more that meets the eye on this. If we zoom in over here, find the 1420 megahertz, zoom in, you can scale off of this, and you can detect that there's a variation of about 1.1 dB over 125 degree C swing, and that comes out to be minus 0.0088. Look at that. It actually agrees. And so this probably is the sensitivity, the gain change for the the Sawbird LNA. And if you convert that over to a power variation, a 10 degrees C change in temperature only gives you about a 2% change in power amplitude, 20 for 4. So this really is a fairly small change in gain over some what you might have on a particular day of temperature changes. And so the idea is, how bad is it? Maybe not that bad. For amateur radio astronomy, a couple percent change in 10 degrees isn't is not that bad. Thoughts?
Please excuse me, I have one thought. Alex,
Yes?
I wish you had saved your data about what it looked like when you smashed your cable.
Oh, what was okay. See, this was since I had no idea what I was doing, I had it seemed simple. This seems like a simple idea. The implementation was really difficult. A few times the thermocouple didn't touch, or putting it in the door and squeezing the coax, I tugged on the thermocouple and it wasn't measuring the body temperature. The other thing is what was happening was, you only know the problem after you've done you spent 4 hours or 3 hours and run all through 4 temperatures and plot it. I was getting drift. I was getting changes. I would measure the signal level at ambient, go through the 2 steps in the refrigerator freezer, warm it back up, and not get the same value. And then I would straighten or touch the cable a little bit, and I'd get a shift. And like, uh-oh. And so I tried to put the cables into the refrigerator freezer in different ways, but either the cables weren't long enough, and at that point, I was suspect that the cables were not going to be sufficiently stable, that I had deformed the dielectric, whatever. And so I threw them away and I bought 2 new cables. And let me see what I did. I have a small cooler, that portable cooler, 12-volt cooler that actually has a compressor, and I could actually recreate the 2 levels of the refrigerator and a freezer in there, and I could put a piece of foam rubber and get bring the coax cables out without bending anything. And so I did this twice, and so I was successful in getting some stable results. And so, but you have to go you have to experience the problem to know how to fix it. And so it took a lot more time than I anticipated, but the data is very consistent. I was pleased I got that level of consistency, and especially when it correlated this closely with published data.
I guess what I'm trying to say is I am so much the person who would damage a cable. I would really like to see a set of data that says this is what it looks like when you smash your cable.
It was just drifting, Wendy. I think as the temperature changed, the cable was either squashed and it started to reform again. It was only you would never know it. You would have to go through all the stages and then see when it's trying to stabilize at a particular temperature that I was getting some drift. I mean,
perhaps this is what other people are seeing when they're talking about excessive gain or drift.
But we're still talking about tenths of a dB.
Okay.
I mean, you're not seeing drifts that would normally anyone would be aware of, and no one puts right angle bends in their LMR 240 as.
Oh, I don't know. I bet somebody does.
Alex, it seems the problem you were having was if you moved something and moved it back, it wasn't the same value you were reading. So it was reliability.
I think Alex just froze. His video stream just quit.
I have a question, comment on this.
Please go ahead.
Yeah, I see on Amazon they have a thermoelectric Peltier refrigeration cooling system for $22. Would it be useful to attach that to the Sawbird to keep a constant temperature throughout the
I
day?
got kicked offline. My ultra reliable internet service died, so I just missed that. Pablo, you had a question?
Yeah. Uh, Maintaining a constant refrigeration could be achieved by using this $22 thermoelectric Peltier refrigeration system for 22 bucks. Attaching it to the Sawbird, and you'd be able to maintain constant refrigeration throughout the whole test.
Yeah, but you're either going to get ice or condensation over a period of time. That's going to be, it would be better if you're going to do anything, you heat it. You maintain it warm, you maintain it above ambient temperature. But with 2 or 3% change over a day, I mean, I haven't seen anyone that is doing any kind of that level of precise analysis that a few percent change in gain would have any influence on their data. But I would go, honestly, I would go hot. If I was going to do anything, I would maintain it at like 100 degrees Fahrenheit. Then you keep it dry.
Yeah, Alex, one more thing to add to your things to do. Coax is also has a pretty big temperature coefficient.
You know, I wondered about that. After going through all this, I don't have long lengths of coax, but I'm wondering if some of the issue that people have described associated with their LNA is not above ground wiring being fried in the hot afternoon sun.
Yeah, and what Wendy was talking about, the crimp actually is very unpredictable because it'll cause the LNA gain to change because of a mismatch. So that can be a real issue. You really don't want to crimp it if you can not do it.
I mean, I don't normally worry about trying to measure tenths of a dB, but in this case, doing it, it brings up sources of error that surprised me.
Well,
I would
once you have
concur.
once you have the 40 dB up front, whatever happens to the cable on its way to the recorder or whatever is really trivial.
Yeah, but
You got a 40 degree crowbar on those changes. However, I wouldn't crimp my cable either.
No, it just happened the way the cables were the initial cables were not long enough that I could go over top of the refrigerator.
It's perfectly understandable. No.
Going in, you wouldn't know it until you did it. It was only
Right.
after doing this a couple times and seeing the drift, then saying, "Oh, the cables must be bending. I must be getting drift from there." It was, you had to see the problem to know there was, even, at least me, in my lack of experience, to have even identified the source of the problem. Took a bit of scratching.
Right. I'm
Yeah,
surprised I'm surprised you might not get more out of that 50 and 60 dB of attenuators.
Well, I mean, everything else was at room temperature, so.
Right. Pretty stable. But
the coax loss is going to add directly to this problem. So the 40 dB of gain up front, that doesn't diminish that at all. It's a noise figure effect that you're thinking it doesn't. The extra coax change
right.
doesn't
It
affect.
is the noise figure.
Yeah.
The other point I would make is anywhere in your chain, any place, do not use Teflon cable. Teflon cable is mechanically noisy as hell. It's awful.
I've never seen that. And they use it in test cables.
Really?
Yeah.
Try
Every
sticking
test
it on
cable.
your guitar cable sometime.
Hey, Don,
Yes.
what would you recommend? If not Teflon, then what?
Well, I just buy good quality LMR 400 or 600.
Okay.
Yeah. But Alex, I would concur with what you found. I've been thoroughly impressed that having the sawbird outside in the sun right on the feed, uh, you get these big temperature swings during the day, and I'd only see a tenth or two, maybe 3/10 dB change on the screen, and so that was really a good thing. I thought these amplifiers were well compensated, and that's what you just proved.
I was amazed. I would never have expected them to be that good. And the fact that I found data sheets and it agreed with what I had done before was really a nice surprise.
Yeah, that's really neat. A neat piece of work, actually. The only other thing that can cause gain changes that you got to watch for is um, your power supply linear regulators. It can put gain changes in uh, on the voltage on the drive voltage for the unit.
Can I show you a couple more slides there? It's
You
related
bet.
to drift.
Yes,
All right.
please do.
Yes, by all means.
Share. Okay, this is not untypical of what I get. I don't know why it's complaining. This is not untypical of what I get during like an 8-hour acquisition session, 5 minutes per sample. If you expand it up, it's like 0.4 of a dB. So it greatly exceeds what the LNA might be doing. And I haven't gone through this, but this is 4 different tests. This is over 8 hours, different days, maybe slightly different declinations, maybe 10 degrees difference between them. But these are the average background level drifts over time, and they're really bizarre. I don't know if the atmosphere, if the water content changes, if it's reflectivity, if it's thermal absorption, but this is what I find happens in all my data, in that this is the raw data set, and I have presumed, and I think it's true, that this is a shift in background level. And what I did in MATLAB, I picked a frequency that was beyond any H1, and I said, okay, I want to make everything equal the lowest. And so this is how I compensate the data before I go through further processing. But this is something that I need to see if I can identify, maybe putting a thermocouple on the LNA and going outside and observing the sky. But I don't know the source for this.
Is some of that explained by passing clouds? That variance.
Clouds are another story, and probably not. In fact, I can't even find the main screen anymore.
Yeah, I just didn't know if in your locale whether you had clouds or whether once it got sunny, it was sunny.
I have had issues with clouds, and that's another thing I want to address sometime and try to do some experiments. In that, I have had no problems with constant sunny days and with constant overhead days. And although water vapor, the 21 centimeter is supposed to be, water vapor is supposed to be transparent to 21 centimeters. There have been 2 or 3 days where there have been these nice white cumulus clouds rolling by, where the sun and my radio telescope were about maybe 20 degrees apart from each other. And what I saw consistently was, if the cloud was over the sun or over the radio telescope, it was the same as a clear sky. As the cloud transitioned, there was a couple dB rise in the background. And I'm getting this suspicion that clouds refract the heat or the RF in that range, that I am getting the black body radiation from the sun is being refracted into the telescope. And it's only the transition. Once the cloud is completely over the telescope, it's fine. When it's completely away, but it's this transition that I could just watch the level go up and down. Walk outside, yep, the cloud is halfway in between, clouds passed.
Oh, you're right. You're right, Alex. That's exactly right.
Is that what's happening? That's strange.
Yeah, it's scattering. Well, it's scattering off the water droplets
Okay,
there.
that's pretty
And
cool.
look up in your Funk and Wagnalls Mie scattering, MIE
Okay,
scattering. It's when the wavelength is longer than the drop size.
okay, I'll do that. That's interesting.
Yeah, I haven't had that much trouble even with rain. Uh, in other words, I've been amazed at how much it could be raining outside all of a sudden, and you still see hydrogen through it. So, the fact that my dish is out normally observing, even, no matter what the weather is, I just don't see that many tenths of a dB change. And if I do, it's probably from the temperature change as the rain starts cooling everything off.
Yeah, this was very obvious, and it was a couple days. In fact, one day, it was a couple Decembers ago, I thought the radio telescope, I could use it as a cloud sensor. It was so incredible because I had the radio telescope set up, and then I had my computer about 20 feet away outside because I was doing some experiments, and it was absolutely perfect. I wish I could have video recorded that. In fact, I want to do that again sometime to show what the sky is doing and what the level was just raising up and lowering. It was on the real-time spectral display of the SDR Sharp Studio.
Yeah, put one of the 12 gigahertz, satellite LNBs on there and try the same experiment. You'll get a lot more change. So it's a lot worse at 12 gigahertz. And you could run that right into the 1420 receiver, actually, because that's usually the IF frequency, 950 to 1450 on the LNBs for the satellite stuff.
Fun stuff.
Yeah, cloud sensors.
Thanks a lot.
Alex, I appreciate what you're doing. You're putting numbers actually to all this stuff. This was what I was seeing with just looking at a resistor. Well, actually, the red line is the resistor. Or actually, in this case, it's actually a non-hydrogen frequency. But yeah, it changes temperature. Temperature messes it up. For a full day, 24 hours, we see this cycle repeat again and again. If at 6 p.m. in the evening, it gets colder through the night, and the amplifiers work better, and so the gain goes up of the same, pretty much the same, well, the same signal. Yeah, no hydrogen in red. And then when it at dawn, it starts warming up the day, and holy cow, the gain really drops. And then sometimes clouds come by in the afternoon, so we get a lot of variance. And that wasn't true just for one day. Here was a bunch of days, maybe at different elevations, but it's the same pattern where at night it goes up and at the dawn it starts going down. Now, my problem here is if I go back to the earlier plot, that the sky I'm looking at with hydrogen is the blue. And it's not like I see a great big bold bump. The bump is not big when the galaxy comes by. And so we care about a variation this large, is what I think we're finding. You're putting numbers to it, which is excellent. So is it the problem with that I don't think I have a regulator out there at this point. No, I was providing power from inside, but I have a long coax going out to it. Is it the coax that is varying with temperature?
Well, you can only attribute 2 or 3% to the Sawbird, and
Yeah, that's fascinating.
everything
We
else
treat-
is something you can't blame the Sawbird for.
That's why I
Yeah,
appreciate
more than
your
a few
numbers. Thank you.
than a few percent. Yeah.
And the Sawbird has a regulator inside, so it actually regulates the voltage down to, I think, 3.7 or somewhere in that voltage range. So it actually takes quite a drop in voltage before it sees it.
That that part, that 9037, it's worth pulling up that data sheet. It's really impressive. It was saying it has some kind of an active bias or something like that to increase its thermal stability.
We put our receiver in a dorm room refrigerator, so I'm not saying that's an expensive regulator, but we saw our gain go up and down every time it turned on and turned off. It was good for beer, which was the main reason for the dorm room refrigerator, but it wasn't stable enough. It was unstable enough that we could see the variation. So then I wonder about Pablo's suggestion of another kind of refrigerator, whether it would be a stable frequency. He was talking about Pelzier, so maybe.
All depends on what you tweak the PID parameters for the on-off. How much dead band and how long you let the temperature change before you turn it off, kind of thing.
Yeah, that feedback loop, exactly, for the temperature control.
Well, those Peltier refrigeration systems can be controlled automatically. So you can set an automatic temperature just by using even a visual program that controls it. Visual telescope programs that actually help control the temperatures. Not difficult at all.
Thank you, Alex, for your presentation. That's great. Glad we got it on tape.
I posted the link to the data sheet on that the LNAs that are in the Sawbird.